Okay, so let's look at some of this stuff here. I want to go over some of this information. Just kind of reviewing back through our momentum formulas and where we use them. Let's look at number 1 here on this, 1 through 6. Let's look at 1 in terms of a car speeds up. So let's match those here. So which one of the formulas over here represents a car speeds up? D. D represents a car speeds up. Well, and why? Well, here we start off with the car and we add an impulse to it, so it's going to end up getting faster. If you put an impulse on something, you put a force on it for a specific amount of time, it's going to get faster. Now, let's look at number 2. A person running catches a football. Where do we see like 2 things becoming 1? And that would be an F right here. If you look at this, we have object 1 and object 2, and it ends up combining over here on this one. We have object 1 plus object 2. There. 2 cars hit and they bounce off of each other. Where would that be at? E. Yeah, very good. E. Okay. And that's because we're going to look at the velocity of one getting transferred to the other one. So we've got 2 objects, and they both have, they're both moving. So we know there's a momentum for that first car, momentum for the second car, and then there's also going to be momentum for both cars afterwards. So that's a good one there, right? A moving airplane drops a bomb. Okay. And where would that go? A. Okay, and why is that one? Well, we've got 2 objects there, object 1 and object 2, and they used to be together, and now they're split up into 2 different things. Okay, 2 different pieces. So that's why on that one. Number 5, a rocket at rest turns on its engine. Hot gases go back, rocket goes forward. Okay, and so that would be C. And then that leaves B for 6. A moving car uses its brakes to stop, and we know the momentum afterwards would be 0. Okay. And then over here with that moving rocket, it started off at 0. It was at rest at the beginning, and then started moving there. All right. So then, number 7, which has more momentum? Okay. Probably a fast baseball. Not probably. It would be a fast baseball. More velocity, more momentum. How about a bowling ball or a baseball, and if they have the same speed? Bowling ball, because it has more mass. A slow ping pong ball or a house? Why does a slow ping pong ball have more? House isn't moving, so its momentum is 0. No momentum there. Okay, there's no momentum. So be careful with that. That's kind of a bit of a trick right there. And then how do we calculate impulse? Good. Impulse would be Ft. And if it were on a graph, if we're on a force time graph, we would want to calculate the area underneath the line. That would give us impulse there. Okay. And that would also give us our change in momentum. You have to remember impulse is equal to change in momentum. Those 2 things are equal to each other. Okay. All right, so let's go on to 9, and we'll kind of run through some of these together until we get to 14. So 9, does a large force always cause a large impulse? No, not always. All right. And why is that? Yeah, impulse also depends on time. Oops. You just have to remember impulse is force multiplied by time. So if you have a large force on something, but it only acts on that object for a small amount of time, like 0.00001 seconds, it's not going to do, there's not much of an impulse on it because it acted for such a small amount of time on it. Okay, so time's also a factor. Let's look at doing a calculation for this then. How much momentum was gained? They give us a force and they give us a time. So how could we calculate that? So you have to remember that your change in momentum is also equal to your impulse, which is equal to F times t. So what's the force? 15 newtons, and the time is 8 seconds. So 15 times 8 would give us 120. Okay, and it's asking for momentum, so we put momentum units on there, and I'll write it down here, 120 kilogram meters per second. So that's not too bad. Okay. So now here we've got an object, one object. Let's see, an object, and it gains momentum. It says how much momentum was gained by the 4 kilogram object. So we have before and we have after, and it was pushed with an 8 Newton force. So how would we figure out how much momentum was gained? Yeah, we need to know change in momentum, which is mass times change in velocity. Do we know the mass of the object? Yep, right here. 4 kilograms. How would we figure out the change in momentum? I'm sorry, change in velocity. How would we figure out change in velocity? Good, final velocity minus initial velocity. What is the final velocity? Well, let's look over here. Can we figure it out from this? Yep. Okay. 36 divided by 4 would give us the velocity, which would be 9. And what was it starting velocity? 3. So 4 times 6 is 24. Now there's another way we could do it, right? We could just take the p after and minus the p before, the momentum after and the momentum before, and 36 minus 12 gives us 24. So there's multiple ways to come up with that answer there. I just wanted to do it a slightly different way, just to show you there's multiple ways to come up with that answer. But the easier way would just go 36 minus 12, right? Okay. Now, how big was the impulse acting on the object? Well, we just figured that out, basically. We did the mass times your change in velocity, which is also equal to your impulse. So your change in momentum is equal to your impulse, which we just calculated that at 24. And we'll just change the units, Newton seconds, on there. If you put 24 kilogram meters per second, that's fine too. Either or. All right, now calculate the time the force acted. Well, how would we do that? Impulse is equal to Ft. So T equals impulse over time. And your impulse we calculated at 24, and the time is, sorry, not time, sorry, force. I did that wrong. Sorry about that, y'all. That should be force. And the force was 8. So the time should be 3 seconds on that. Okay. And make sure you change this formula here. Now calculate the acceleration of the object. Just come back to F equals ma, right? And then so acceleration is equal to force over mass. Do we know the force on this object? 8. And we know the mass was 4, so 8 divided by 4 is 2. Okay, just some review there. All right, and then what is the final velocity of our object? And we figured that out up here already. When we did the 36 divided by 4. We just used your momentum as mass times velocity, and then we did velocity as momentum over mass, and we did 36 over 4, and that is 9 meters per second. Okay. If you look at 12 on this one, they can have more than one. If we're trying to determine if we're looking at elastic collision, is it an inelastic collision, or perfectly inelastic, that is they stick together. Let's find one that's perfectly inelastic where they stick together. Which one do you think is perfectly inelastic? Okay, definitely C. This one is perfectly inelastic. And I'm just going to put a PI. It's not a specific abbreviation for it, but it's hard to write perfectly inelastic into that little tiny space. And you can do the same. But you can see afterwards right here that those two things stick together. Okay. How about number 1? Well, that one could also be perfectly inelastic, but that's not our only option. There. Let's look at that. If the momentum before is equal to the momentum after, that could be perfectly inelastic, for sure. Especially if there's some heat loss, so the energies are not equal to each other. With perfectly inelastic, we'll always see energy lost, as well as, energy lost, as well as inelastic collisions too. So with inelastic and perfectly inelastic, we'll always see energy lost. So guess what we look at B? Could B be inelastic or perfectly inelastic? No, because the energy is not lost, it's the same before and after. So this has to be only elastic. All right. A could be either inelastic or perfectly inelastic. That could be either or. Now, let's look at if there is little or no sound created during the collision. What do you think that one might be? Elastic. Yep. Because it takes energy to make sound, right? So energy would be lost out of the system due to sound. So if there's a lot of noise, that could be inelastic or perfectly inelastic. Either one. How about if the objects are mangled or crushed up? Definitely, that's an option, perfectly inelastic, or it could also be inelastic. Okay. How about number 13? Two objects collide, they don't stick together. What happens to the momentum of the 4 kilogram object? Two objects collide. Don't stick together. We can see that this has a large velocity because the arrow is bigger. This has a small. Yep, good. The momentum here will increase. It's going to end up going faster. So if this one ends up going faster and this one increases, then what happens to the 6 kilogram object? We have to decrease. So this decreases. Okay, and the total momentum of the system remains the same.